It's so cool.
Amazing.
It's amazing.
Oh my god.
Wow.
This is super cool.
Hello, and welcome to Stir Fried Fascination. My name is Rasmus, and I'm fascinated by almost everything. How the brain works, cave paintings, the history of robots, why some cheeses are smellier than others, really tall people, and Belgium. Today, I'm going to learn about quantum computing. And whom better to ask than John Martinis, who actually built one, and not just any old half-priced one. Him and his team at Google built a quantum computer that could beat a supercomputer. Amazing! John is a professor at UC Santa Barbara, and his work on quantum supremacy has been covered in Nature, IEEE Spectrum, MIT Tech Report, Wall Street Journal, and lots of other media outlets. Now let's get started. Hey John, how are you doing?
Well, I'm doing fine. I'm going to enjoy the conversation this morning.
So, what inspired you to get into quantum computing in the first place?
Yeah, that's a good question. When you take physics and you start learning how nature works, one of the most fun classes you take is quantum mechanics, because it's this very strange and non-intuitive phenomenon.
Yeah.
That is, of course, very important for the modern world because we have to understand how atoms work. And so you take that, and it's exciting. It's very strange. It's very mathematical.
Do you actually enjoy that, though? Do you enjoy the mathematics of it?
Yeah, I mean, it's different mathematics, and part of the problem is that you're used to kind of classical things, how it works around you, and you gain an intuition for how things work. But all that intuition really doesn't help you necessarily too much when you study quantum mechanics. So you kind of have to understand both from a conceptual level what's going on, and then from a mathematical level, which of course is what we try to do in physics, is describe things that way. So it's really this great place where great subject where you learn new things different way. It's very surprising. And the nice thing about quantum computers is it kind of simplifies quantum mechanics, where you're talking about, simple qubits or whatever, and you get to understand quantum mechanics on a very fundamental and almost abstracted way, so that you can really get at what's going on deeply. And then, of course, once you do experiments with a quantum computer for, years and years, it just seems totally natural, just like, dropping a ball and watching it, fall to the earth. Well, when you do quantum mechanics and you're playing with it all the time, then it just becomes
used to it.
Yeah, you get used to it, and it's not so strange anymore. I mean, it's still strange, of course. It's still different, but it doesn't seem that unnatural anymore. And that's what I think is kind of great about quantum computing. It's a nice vehicle to really understand quantum mechanics much more deeply. And that's what's happened over the last 10, 20 years or more that I've been in the field, is people can do these more and more probing experiments that makes physics so interesting.
Yeah, and I guess, of course, the more you play with something, even if you don't exactly understand what's behind the thing you're using, the more intuitive it becomes anyway.
Yeah, and it's also interesting to see that, humans are pattern recognition machines. So if you play with something and you see a pattern, you say you understand it. But of course, in science, you say, yeah, okay, you can understand the pattern, but you have to understand the mathematics and the detail, what's going on. And that's what's great about physics, is you're trying to match the patterns you're seeing all around you with some mathematics and a deeper understanding.
Right. Yeah. I was thinking about it before also. A lot of people focus on the fact that quantum mechanics is kind of strange.
Right.
But on the other hand, humans have believed in a lot stranger things in the past. I mean, elephants with several arms that are gods that live in the sky. There are, minotaurs, horse people. So, like on the larger scale of things, it's not that weird.
Well, yeah, and if you look at the history of computers, I'm old enough now that when I was a young person, computers were these strange and mysterious things, And,
Right.
not very many people understood them in that sense. And yet, when you
No,
saw
yeah.
my boys growing up and they started playing with it, and they started programming when they were, I don't know, 12 years old or so, by
Yeah.
going online and looking at courses and downloading things. And, you can kind of just learn it on your own almost now. So, yeah,
Yeah,
things,
yeah, for
things
sure.
get different once you can start playing with something and
Yeah.
seeing how it works. And of course, it interests you and you're motivated to do that. And I think that's what's going to happen more and more with quantum mechanics as we build these much more sophisticated and maybe easy to use quantum systems. People have talked about this, that really computer science and the whole industry of software really blossomed immensely when people could start playing with computers and they got cheap enough. So
All right. Yeah.
yeah, in that's what we're hoping will happen with quantum computers too.
Mm.
Is we have to build these things and learn how to use, but as more and more people can learn how to program it and use it, and who knows what inventiveness will come out.
But what sort of stage are we in right now? Are we like comparable to the old Colossus computer that
Yeah,
was
yeah.
used
At the
in?
very first quantum computers,
Right. Yeah.
yeah, very first computers. We're at that stage, and I'm going to say the computers at this point are pretty rudimentary. And I would say the quantum supremacy experiment we did at Google was kind of unique in that we were able to do something to show the power of the quantum computing. It is a
Mm.
very much crafted problem. A lot of
Yeah.
people say it's not useful. I think it's useful, but it's kind of more subtle things that it's useful for. But
Right. Yeah.
kind of the first time that you really showed the power of it. And of course, by showing that a quantum computer can be powerful in the sense that you can't reproduce the result with a supercomputer,
Mm.
then people see that this is not just some physics pipe dream, but
Right.
actually. So I think it's created a lot of industrial effort
Let's just
and interest.
let's just try and simplify that for the audience as well.
Sure.
So this quantum supremacy thing, what it's about is basically proving that you could make a quantum computer that could be better at something than
That's
a normal supercomputer.
That's correct.
Uh,
And it's
right.
powerful, and the way it's built, it's if you compare it to a supercomputer, it has a
Hmm.
relatively small number of qubits compared to bits,
Right. Yeah.
and it's
For sure.
relatively small. I mean, it's a sophisticated scientific instrument, but to have this rather small machine being impossible to reproduce with the world's biggest supercomputer, I mean,
Mm.
that kind of tells you there's something fundamentally interesting and important.
How big is it? How big
Oh,
is the?
it's the size of. I'm looking in my kitchen right now. I'm looking at my refrigerator. It's the size of 3 or 4 refrigerators, say.
Three or four refrigerators.
Oh,
Yeah.
so it's
Okay.
not
Cool.
tiny like your laptop,
Yeah.
but it's comfortably fits in a room, and
Mm.
you,
Yeah.
you can work on it yourself.
I was actually thinking about refrigerators earlier as well today because here I am going to talk about quantum computing with an expert in quantum computing, but I'm actually fascinated by all sorts of technology. I mean, I don't know how my refrigerator works either. So that's kind of interesting. I don't know how my vacuum cleaner works. But on the other hand, like vacuum cleaners don't have a sort of Moore's law where they sort of get better and better exponentially.
Yeah, right, right,
So
right.
they're not as interesting to look at as, and they don't have this sort of strange, mysterious part to them either as like
Yeah,
quantum
and
computers do.
and that's what's interesting, of course, about quantum computing is it has this strange new uh, power in it, which
Hmm.
basically comes from some kind of parallel computing that you're able to
Right.
do
Yeah.
on a quantum computer, which it's hard to
Yeah.
take advantage of. You have to write good software to take advantage of it, but it's a
Mm.
really a new concept. And that's why it's just so new and so weird. That's why people always thought that this was going to be a pipe dream and not reality,
Right.
because it's
Exactly.
hard
Yeah.
to imagine that's going to do something. So that's why we did the experiment, is to
Mm.
really show people. It's kind of funny though, the physicists expected it to work. Although
Yeah.
I think a lot of people thought, well, it's going to take quite a few years to get it to work.
Yeah.
So we did
Yeah.
it faster. But I think
Yeah.
for the normal technologists, let's say Silicon Valley executive, Google
Mm.
executive, it's like,
Yeah.
oh, okay, you say that's true, but can you really get it to work? And
Right. Yeah. Exactly.
and that's important. You have to show things. And I would say the other thing that happened is there's a lot of basic science that you don't know if it's going to work if you build a complex system or you do something like that experiment. And this was
Mm.
also a big test of science and the validity of quantum mechanics, and does it work in a way that it has to work to build a
Yeah.
quantum
Exactly.
computer. And
Right. Yeah.
it's possible that it would have failed, either from
Mm.
fundamental or practical reasons. And as scientists, you have to test things.
Right. I think you have a colleague called Scott Aronson. I saw him on
Yes.
YouTube when I was trying to figure things out, and he was saying that it would actually be way more interesting if it failed, because then we'd
Yes,
sort of
of
learn
course.
something. We'd learn something new about quantum physics.
Yeah, but in physics, physicists are always pushing the boundaries of what we
Mm.
know. And
Yeah.
you have some phenomenon, and you change it a little bit, and you see if it's real valid. And
Mm.
it's a very important part of physics. And of course, the most important things happen is when it doesn't work, as Scott says. But
Yeah.
what was interesting in the quantum computer is up until our experiment, people had done experiments. They were doing this parallel computing of about 1,000 states. So imagine a computer, and you have, like, let's say 1,000 laptops that are solving a problem simultaneously. Okay,
Hang
so
on,
so
hang on. Maybe before we get into this, we should actually explain sort of a little bit about quantum computing. Maybe this is a good time to get into what parallel computing is and all that. So, if you take it away, like from the top, what is a quantum computer? How do they work?
yeah, so to understand the quantum computer, maybe we can first start a little bit about how atoms work. So
Hmm.
let's just take a simple example of the hydrogen atom, which is the simplest atom there is. And
Right.
that consists of a proton, the nucleus, and then an
Mm.
electron, which is orbiting around the nucleus because it's so much lighter. And
Right.
if they're of opposite charge and they're going to attract each other, kind of like
Hmm.
you think with gravitation, with gravity, which you all understand.
Mm.
Now, the strange things is if you had an electron attracted to the proton, they would just stick to each other. And you
Right.
would
Yeah.
ask, well, why do atoms have size? Why does matter around us have size at all if these two fundamental particles just want to stick to each other?
Right.
And
Yeah.
you need to have some strange non classical physics going on just to explain the world around this and why material have size. And clearly, if there was not quantum mechanics, we
Hmm.
wouldn't be here. I don't know what the world would look like, but you
No.
actually need quantum mechanics. And what happens is quantum mechanics says is this motion of the electron. It's no longer like a point particle anymore. It's what
Hmm.
I used to tell my kids is that the electron is fuzzy. Okay, it's
Right.
not a point particle. It has some size to it in a kind of a very strange way. So they always
Mm.
laughed when I said that because they never believed that electron,
Right.
which is great. I had to give them better explanations, but of course that's hard.
So the atom has size because you're saying because there's this electron which is fuzzy. It's not in one place.
That's right.
So if it was in one place, it could somehow decide to, well, actually, I'm just going to follow classical laws and I'm just going to
It
uh,
get attracted
go
to the proton, and
the
then
attractive proton and stick to it.
and it wouldn't do anything. So it has
Mm.
some good spatial extent. Now, what's interesting is people often think quantum mechanics, you have something called the
Right.
uncertainty principle, and like the electron
Hmm.
is jumping around in some fuzzy way around the proton. But it turns out quantum mechanics doesn't work that way. It's actually a very, very
Hmm.
precise motion. Okay. The motion is through something physicists study called
Right.
waves. And for example, if you pluck a guitar string, there's going to be a wave in that, and the guitar string is oscillating back and forth in a
Hmm.
certain pattern. Okay. And at the two ends of the string, it's not moving at all. and kind of in the center of the string, it's
Right.
moving the most. And it turns out that matter and electrons kind of behave in the same way, where they have this, what we call a standing
Mm.
wave pattern, like a guitar string, that it's
Right.
oscillating. And it's a very well defined kind of oscillation, just like the note has a very well defined frequency in a string.
Right. But this is kind of different here because we're talking about a wave that relates somehow to probability, the probability that if we measure it, it's going to be in one specific place, right? Is that correct?
That's right. So if you look at the
Yep.
guitar string analogy, then
Mm-hmm.
where the wave is the biggest, it would be the most probable to be there. And at the
Mm-hmm.
ends of the strings where it's held tight, then the probability is going to go to zero at the two ends. So
Right.
there's this strange, kind of thing you have to understand about quantum mechanics, that the kind of the amplitude of the wave tells you the probability. And then that's kind of the fuzziness, is that this wave has some extent, across the atom.
Right. Exactly. So the wave function basically decides sort of where it might be,
That's right.
and but we
But
don't
the,
know actually
the
what's
important
going
thing
on.
is that it's very well defined
Yeah.
wave property. And, people make atomic clocks out of these oscillating waves that are
Mm-hmm.
accurate to a part in, I don't know, 10 to the 16 right now. It's very, very
Mm.
accurate,
Right.
extremely precise. And in some sense, it's some of the most precise things we know about nature
Mm-hmm.
is how well defined these oscillations are and these waves are. It's really kind of
Right.
remarkable how that works.
Yeah.
If it's very well defined, and we know the mathematics on how it's well defined,
Mm.
then we can use that phenomenon for doing precision experiments and measurements. So you make
Right.
clocks for your GPS, and you can
Yeah.
also build a quantum computer out of it, because the motion of these quantum systems are very, very precisely known and can be predicted. And one can
Mm.
build a whole logical structure out of that.
Right. So basically, this is how I understand it. You don't actually know what happens when you're not actually measuring where the electron is.
Well, that
But
actually, let me be a little bit more precise, okay?
okay.
What
Yep.
happens is you manipulate this state, and
Hmm.
it's obeying quantum mechanics, and you actually know what's happening with it. You can predict it. There are mathematical equations
Yep.
and all that. So it's extremely predictable, which is, of course, what you
Right.
need
Yeah.
for a computer.
Yeah.
However,
For
you
sure.
go measure it, and you want to know, okay, what's really going on with the quantum system? Where is the electron?
Yeah.
Then, when you measure, is where you have uncertainty. It can be sometimes here or
Mm.
sometimes here.
Right.
So,
Yeah.
so what happens is you can predict what's happening with the quantum system very,
Mm.
very precisely, until you go ahead and you try to extract information and measure it, and then
Right.
you get a probability out of it.
And it's that prediction that we know something about, right? It's that prediction that we're precise about.
That's right. And what
Right.
happens with the prediction, since it can have several outcomes, you get a probability. So sometimes it's going to
Mm.
be here, but sometimes it's going to be here. And when you
Mm.
measure it many, many times, you get some probability distribution. And that you can compare very precisely with theory.
Right. Yeah. So how do you actually use this to build a computer?
So what we do is we take, I'm just going to use the hydrogen atom as an example.
Sure.
So the hydrogen atom, if the normal state is in its lower energy state, which in
Hmm.
some orbital language is the 1s state, okay, which just says
Okay.
it has a certain wave to it,
Yeah.
okay, and we encode that to the zero state of a bit or quantum bit. We talk about quantum bits when we start talking about quantum mechanics, but in analogy, this would be a zero, okay, which is going to use some information. And then if you go to an excited state, so if
Mm.
you look at your guitar string, that would be an overtone, and then you encode that as a one. And then
Right.
so you code it with the quantum states. And then
Mm.
what you could do is you could put in pulses of light that would cause
Mm-hmm.
a transition from one state to the other,
Right.
changing the frequency of the guitar string.
Mm-hmm.
And then that would be equivalent to doing a manipulation of the logic state from a zero state to a one state,
Right.
just like
So
you do with a classical computer. Hey, you have zeros
right.
and
Yeah.
ones. And one of the operations is to change it from a zero to one. And on a
Mm-hmm.
classical computer, one of the operations is to have two bits and have those two bits interact in some way to give you an output. So you do a similar
So
thing with quantum
if you
mechanics.
just have these two states, then it's going to be like an ordinary computer, basically.
Well, yeah, what'll happen, of course, it is a little bit different because in an
Mm-hmm.
ordinary computer, you could put in a zero to an algorithm and run the algorithm and get an answer. And then
Yeah.
you would put in a one into an algorithm and get the answer. But you have
Mm-hmm.
to run it twice, right? With a quantum computer, you could um, put in a state that's both zero and one at the same time, run it once through the quantum computer, and
Mm.
then get some answer out of it. And because of that, you get this kind of parallelism out of the quantum
Mm-hmm.
computer. Uh,
Yeah.
Now, how to measure it and what the algorithm is, that's very complicated. Okay.
But wait a minute, John. Let's get into this parallel computing a bit, because I'd like to understand this a little bit better. This is how I think about it, and I think, just correct me if I'm wrong. I draw a parallel to the English language. So in the English alphabet, we have letters that combine into words. So if you want to write the word house, you need to use a combination of
Right.
letters. On the other hand, in Chinese language, you can use one sign for house. So if you wanted to change the word house in the English language to some other word, let's say table, then you would have to do operations on each and every letter one at a time, basically. But on the other hand, if you would take the word house and then translate it into Chinese first, which is one sign,
Right.
then you could do one operation on that sign and change it into table, the Chinese word for table, and that would only take one operation. You wouldn't have to change a bunch of letters. You would just change that one sign, and then you would have to translate it back to English again to get the answer. Uh, is that a good parallel to what's going on?
Yeah, it's an interesting parallel. I hadn't thought of this.
Mm-hmm.
It kind of is an idea of using coding, which in data compression. That's a better word,
Yeah.
where
Right. Yeah.
you compress it to this Chinese symbol. And
Right.
I
Yeah.
would say that quantum mechanics is different than data
Mm-hmm.
compression. Okay,
Okay.
so
Yeah. Yeah.
it's an
Yeah.
interesting analogy, but I'm not quite sure
That
that's
it works.
so. Let me explain. Maybe you'll understand why this parallelism is so important. So with one quantum bit, you get a parallelism of two. Okay, and which is nice, but okay, I can just run my classical computer twice. It's fine.
Mm.
But
Yeah.
what's interesting and profoundly important about quantum mechanics is the way that it scales. So, I'm thinking of an analogy you might like here. So, if you
Mm-hmm.
have two quantum bits,
Yeah.
and then they're each in a superposition as zero and one, that means you're actually running four states at the same time: zero, 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 one, one, zero, and one, one. Okay.
Okay.
And if you have three qubits, it's 000, 001, 010, 011. Then there's eight states. Okay.
Mm-hmm.
So
Right.
every time you add a qubit, you're doubling the number of parallelism,
Right.
which means, it's growing what we say exponentially. It's growing very, very large.
Somehow this still seems like compression to me. Somehow this still seems like you can encode more information in a smaller bit than if you would use a classical computer, because you have more combinations, right? That's the main sort of geist of it, right?
And this is what happens in classical computers is you make bits into bytes into longer words. You can
Mm.
encode more and more complex information, which we all know about in our computer. But the
Yeah.
problem is in a classical computer, as you make the bit strings longer and longer, you still have to process that information one unit at a time,
Hmm.
one byte at a time, one word at a time, something like that.
Right.
Whereas in a quantum computer, you could process all the information. So you take house and table and chair and
Hmm.
a ton of words,
Yeah.
and all of those words can get processed in parallel, right?
Right. Yeah.
And you can convert them into Chinese and then back again, all in parallel. You don't have to
Mm.
do it, 1,000 times. You just do it once.
Okay.
Your
Well,
analogy
can we?
is talking about the how powerful it is to string bits together to make things more and more complicated. What the
Mm.
quantum computer says is as you make it bigger and bigger, it's still you can make it into one operation. You don't have to do it.
Mm.
You can process house and table and chair in one operation.
Right. This is where it gets very strange, though.
So that's what's wonderful about it.
Yeah,
Exactly.
exactly. And I guess that's why you constantly want to try to find parallels in the normal universe to sort of try to wrap your head around it. But then it sort of escapes your normal parallels anyway. Uh, right. So I think I kind of understand what you're getting at. And I think what we're going to do is to take a little break on the understanding of the quantum computer, because I think for the audience it gets a little bit heavy if we're going to move on to the next concept now and explain, let's say, quantum cooling or something like that. So let's try something a little bit lighter in the meantime.
Sure.
Uh, so what are these for? What do you use quantum computers for?
Well, you use quantum computers for doing computational problems, just like
Right.
the fundamental idea here is we know computers are so important. If there's a new way to do computing that's potentially way, way more powerful than what we know how to do now,
Mm.
well, we should just be investigating that. And I think part of the reason people think about this now a little bit more is there's Moore's law that says that the computing power is doubling every so many years, but
Mm.
as things get more and more complex, it's harder to keep on improving the performance over time in the way. And
Right.
of course, if you have anything exponential, at some point it has to stop. Okay, so
Right. Yeah.
so
Yeah.
people are looking at alternatives to it. Now, that
Mm.
all being said, I think people understand with a quantum computer, it's not going to be as general purpose as a regular computer. But
Mm.
there's enough algorithms out there that people are excited that it would be doing something. And of course, people didn't necessarily expect all the amazing things you can do with a classical computer.
No, exactly. Yeah. Yeah. Right. And there's also like classically, I mean, there's also a lot of things that we didn't expect to be interesting when they were invented. Let's say the laser or
Yes,
even the telephone, like the mobile telephone when it came. A
yes.
lot of people didn't really think it would be as big as it is.
Maybe Steve
Mm.
Jobs knew, but a lot of
Yeah. Exactly.
Uh,
Yeah.
but yeah, and it's what I like about it. It's a very important scientific quest where we
Mm.
can build it and see if we can operate quantum mechanics in this way,
Right.
as well as something that could be very practical.
It would be really nice to hear some more specific ideas.
So let me talk a little bit about quantum chemistry. And,
Right.
and the reason I like to talk about quantum chemistry is, my personality is such I really like to think about, definite ideas. And I think quantum chemistry is a very definite application that's real. We're going to do it. It's going to be very helpful. As long as we can build a quantum computer.
Right. It's certain. Like we know that that's going to happen if we can build a quantum computer.
Basic idea behind this is actually kind of simple is we
Mm.
know that atoms and molecules are put together by quantum mechanics.
Right. Yeah. Of course. Yeah.
You could think about mimicking that quantum mechanics with another quantum system, mapping a quantum chemistry problem onto a quantum computer. This was
Mm.
first kind of hypothesized and brought forward by Richard Feynman in the early 1980s. But what was interesting is that, it was early 1980s, but it was only in the mid 2000s that people started to understand that mapping. I mean, it's really complicated. And then, there was a first mapping that people did, and it was extremely inefficient, so that you would never expect a quantum computer to be able to solve a realistic problem. But what's as usual in science is people started looking at all the assumptions and figuring out ways around it and blah, blah, blah. So that now, in let's say a space of about 10 years or so, people learn how to do the mapping efficiently so that we now think we can do it. And what happened is there's people at Google working on the theory of this. They're projecting if we can build everything right at 100,000 to a million qubits, we could start solving quantum chemistry problems for real that we can't solve today. That's, clearly far away from where we are now. But
Sorry, I missed how many qubits do you need for that?
we need about 100, say 100,000 qubits, and the qubits have to be better than what we're doing now.
Right. Yeah.
You need to do error correction, need to do these things. Now, that all being said, people have been doing quantum chemistry with qubits, and we did one was about 5-6 years ago, and other people have doing it. And the Google group just submitted kind of the most complex problem in a paper just recently. So it's way more complex than whatever has been done before. We're practicing the algorithms. There are some new clever things that they've done there to get it to work. And, people will be, investigating this more and more and showing that it's a real application. They're doing real experiments now.
I'm going to ask you kind of a silly question, but I'd like to ask you anyway. Can you get a virus on a quantum computer?
Yeah, that's something I haven't thought about. That's a good question.
Oh, really?
Yeah, I have no idea. That's a really good question. I don't know, what you would do with it. I mean,
No.
if you want to kill the quantum computer, you just cause something to add more noise, and then
Right. Yeah.
so easy for it not to work that
then to work.
being so careful about it working. But it's probably like every other software, and you have to be careful about what you're running and whether it's doing sensibly. But it's you're going to use a classical computer to talk and control a quantum computer, so it's much more likely that the virus is going to be in the classical control than it is in the quantum computer. I think there's much more opportunity there. Oh, that's fun though. Thank you. That's a good question.
And that's it for now. John has so much more to say about his tallying gadget that it got a little bit long for one episode. So I decided to cut the podcast in two, kind of like splitting a really good grapefruit, or an atom, or a piece of cake that becomes two pieces of cake. And if you have a question for John, then write your question in the comments field for this episode. And if you want to see more, don't forget to like and subscribe. And while you're doing that, why not also open your window and just shout out the name of my podcast, Stir-Fried Fascination! Thanks for listening, and see you in the next one.